Today's lesson is on structural member properties. Module of elasticity, and we use the letter E to represent a capital E, represents the ratio of the increment of some specified form of stress to the increment of specified form of strain. So basically stress divided by strain. It's also called the coefficient of elasticity or elasticity modulus, or sometimes called the elastic modulus, all different names for the same thing. It defines how stiff something is relative to its chemical properties. For example, on the left-hand side, we've got a diving platform, which is very, very stiff. It's not designed to bounce. And on the right-hand side, you see a springboard diving board, which is less stiff. It's designed to be flexible. In general, a higher modulus of elasticity produces greater resistance. Again, it's going to be more stiff, greater resistance to being deformation. Okay, we got two planks here. A is Douglas fir, which is a type of tree. And we've got, the second one is ABS plastic. Basically, it's plastic lumber. Notice they both have the same width and height. They're both 2x6s. They both have the same cross-sectional area. And they both have the same I. Okay, you learned how to calculate I, which is a moment of inertia in the last lesson. What's the key property that distinguishes A from B? Okay, well, again, it's the material. A is wood, Douglas fir. B is plastic, ABS plastic. Will beam A or beam B have a greater resistance to bending, resulting in the least amount of deformation if an identical load is applied to both beams at the same location? So what do you think? Do you think that the wood is going to bend more, or do you think the plastic is going to bend more? Well, you can see from this diagram, right? It looks like the Douglas fir bends quite a bit less, okay? And the plastic, which is the one farther in the background, bends quite a bit more. Why did beam B, plastic, have greater deformation than beam A? Well, they have a difference in modulus of elasticity. That's that E, which is the ability for a material to deform and return to its original shape. The characteristics of objects that affect its deflection or bending is represent a couple different things. The term deflection is measured as delta max. The triangle, the symbol you see right there, is a delta, which is change. Okay, basically that's the max deflection, or how much the maximum bending you get. The maximum bending is always going to be in the middle and not at the end. So that's where you're going to measure maximum deflection. The things that will affect deflection include the amount of force. An elephant is going to bend it a lot more than a 5-year-old. Okay, also the length of span between supports. If it's a very long bridge, it's going to bend a lot more than if it's a very short bridge. Like a log just going across a short stream, okay, is not going to bend as much if it's that same thickness of a log was going off a very wide river, such as the Hudson River. Many of you have probably seen the Hudson River. You know, modulus of elasticity obviously affects deflection, and also the moment of inertia affects the amount of deflection that you're going to get. The way we calculate beam deflection, again, is that delta max, and that formula, this formula you don't have to memorize, it's on your formula sheet, is equal to F, which is force, times the L cubed. L is the length of the beam, L cubed, divided by 48 times E. Now, E is that modulus of elasticity. That you have to be given that. You can't, in order to be able to plot. You can look it up based on the material. You can look up Douglas fir and get an idea what it's going to be. And then times I, which is the moment of inertia, which again, you calculated last time. You learned about that last time. So in order to calculate beam deflection, you need to be given the force, the length, the modulus of elasticity, and you also need to be able to calculate out the moment of inertia I. So here are those properties. We're given the length is the same for both beams A and B. The moment of inertia, we said, is also the same, and the force is the same. So 250 pounds. The only difference is E. Okay, the modulus of the E for Douglas fir is much bigger. Okay. Bigger means it's going to be stiffer and it's going to bend less. ABS plastic, the E is smaller, which means it's going to bend more. So let's calculate the beam deflection. Okay, force is 250 times L cubed, which is 96 inches cubed. Remember, length has to be in inches. If I is in inches, length has to be in inches. So you need to convert your length, which will usually be in feet, to inches, divided by 48 times E, which is 1.8 million pounds per square inch, times 20.8 inches to the fourth. Let's do the math, and we end up with 0.12 inches. So basically, our joist, which is our beam standing upright, is going to have a max deflection of 0.12 inches for the Douglas fir. Now, all those numbers are exactly the same other than E for the ABS plastic. So you'll see all those numbers are going to be the same other than E. Okay, all right. So again, it's 250 times 96 cubed divided by 48. But in his case, the E is 419,000, so a much smaller number, times 20.8 inches to the fourth. So we're dividing by a smaller number, which is going to end up with a much larger deflection. So the deflection is 0.53 inches, so significantly larger. What I think it's 3 times, about 3 times as much deflection. All right, ooh, more than that, more than 4 times. So 0.12 as opposed to 0.53. Again, that's why the plastic bends much more, is because it's got a much lower modulus of elasticity E.